Hi everyone. I've got one more video to record, which is just going to be the difference between isothermal and adiabatic. And whoops, I must have somewhere in the video stopped recording, so I missed out on giving you a little information about this last question. So I want to backtrack really quickly and make sure we cover this one, because this is a really intriguing idea that I want us to all think about for a second. So we have isobaric and we have isochoric. Isobaric, constant pressure, isochoric, constant volume. And basically it's saying we have one of those two scenarios. Keep the pressure the same, keep the volume the same. But what if you want to change the temperature? Which one will require less heat in order to do it? Which scenario requires less heat to flow? Well, only thing I can do is draw a quick picture. So in both of these scenarios, it says PV. We'll make it purple for the constant pressure. Constant pressure, okay, I'm going to have a horizontal line, meaning the volume changed. Constant volume, I'll use green, okay? That means I got a vertical line, just like that. All right, so which one will require less heat to have a change in temperature? Let's also think about it in terms of equation. We said that the temperature is related to a change in internal energy. And we said our internal energy, or a change in internal energy, is related to the amount of work done and the amount of heat flowing in or out of the system. Well, let's look at first our isobaric, constant pressure situation. In our isobaric situation, I have the work being done. And then remember we said if I'm going to have the same pressure, even though I'm changing the volume, the only way to do that is to maybe put it under fire or put it in an ice bath. So for isobaric, you're going to see both work and heat going into the system. Isochoric, however, there's no work done. And so if there's no work done and the volume stays the same, we have to rely on just the heat flowing in and out to change our pressure, because the volume stays the same. And I should say to change our internal energy. So let's look back here. I'm going to label them really quickly for us. Isobaric, isochoric. Which one will require less heat flow? Well, it's the one that also has work being done. Because if no matter what, I'm going to increase the temperature, I'm going to increase the internal energy. How am I going to do that with isochoric? With isochoric, all I have is heat flow. There's no work being done because the volume never changes. The volume's fixed right there, so no work is done. So I have to have lots of heat flowing in. In isobaric, pressure is going to stay the same. So the way I can achieve that increase in internal energy, that increase in temperature, is going to be by changing the volume and then by having just a little heat to add to the system. So if you desire to change the temperature, which scenario requires less heat? Isobaric. Isobaric requires less heat. Why? Listen up. If you don't know the why yet, listen up right now. Why does isobaric require less heat? Because some of the internal energy change happens thanks to work, thanks to changing the volume. Isochoric takes more heat because the volume is fixed in place the whole time. So all I have is heat to add into the system. Whew. Let's finish up with isothermal and adiabatic. All right, isothermal. Internal energy change is proportional to temperature, and thus the isothermic scenario we can conclude. What about the internal energy? Well, if the temperature is going to remain the same, so is the internal energy. In all of these scenarios with isothermal, what's going to happen is we're going to change the volume and we're going to change the pressure. Temp stays the same. We're going to put work in, or we're going to take work out. We're going to add heat, or we're going to remove heat. But no matter what, the delta U is going to stay the same. These variables will change so that these can remain constant. All right, how is work done if the temperature and the internal energy remain constant? Okay, this is a big deal, and this is going to be another scenario where you're going to need to have probably a red and a blue pen for your Bunsen burner and your ice bath examples, okay? So get your red and your blue pen ready for those examples. I'm going to start off by drawing my PV diagram. And it says, okay, the temperature is going to stay the same and the internal energy is going to stay the same. How is that possible if work is being done? Well, for my first example, I'm going to have the volume gets smaller. Now, test question for you, friends. If the volume gets smaller, is that work being done on or by the gas? The volume is getting smaller. Is that work being done on or by? You need to know the answer to that one. I hope you said on the gas. Yeah, as the volume gets smaller, work is being done on the gas. So work is negative. All right, well, if work is negative as I'm pushing on it, then that means what? We got to put this thing. Oh, man. I didn't write it down, so I don't know which way I said it. I hope I said as work is being done on the gas, that work is positive, but I'm afraid I might have said it backwards, and I'm too deep in this video to just restart over. So I'm going to just make sure we write it down right now. The volume is getting smaller. Work is done on the gas. That work is a positive number. Do my distinction just like that. I'm also going to put a little line down the middle because I'm going to have to do my counter example over here. So, work is done on the gas as the volume gets smaller, and it's positive work. But I need my internal energy to stay the same, so that means I got to put it in an ice bath. All right, I've got this gas here. I'm making the volume smaller, and by making the volume smaller, following this little path here, that's going to make the pressure go up. But the thing is I need the temperature to stay the same. So as the pressure goes up, the only way I can make sure that the internal energy stays the same, make sure the temperature stays the same, is to put it in an ice bath. So I'm going to make sure that the ice bath causes heat to leave the object. I find it's funny that I'm writing ice bath with a red pen. It goes back against everything I've been talking about with color coding. Oh well. So now there's something interesting to be thought of right here. It tells me that I need the internal energy to remain constant. The internal energy to remain constant. The only way that the internal energy can remain constant, The only way that my delta U can be equal to 0 joules is for my work and my heat to be equal to one another. And so I'm going to go like that right now so I don't have to worry about that question. My absolute value for my heat in this situation, leaving the system, has to be equal to my work being done on the gas. Those two absolute values are equal to one another, which allows us to have a constant internal energy, or a change in internal energy that equals 0. One thing to note, everywhere on this line here, every point on this PV graph, the temperature is the same everywhere on that line. Shouldn't have drawn on it while I was holding it up in the air. Everywhere on this line, the temperature remains the same. Doesn't matter. Pick any point. Temperature is the same. Pick any point. The temperatures are the same. Because as pressure is going up, as volume is changing, as pressure is changing, the temperature remains the same. All right, let's do our counter example, and let's talk about what happens when the volume's getting bigger. So we're about to put it in a Bunsen burner, so if you're really clever with your color coding, you would use red pens here, because we're about to use some fire. I totally broke my color coding system right there. It's too late now. So now all of a sudden, same picture, same idea, except now I'm going to be pulling outward. And as the volume gets bigger, work is being done by the gas, and that work has a negative value. So work is being done by the gas, and that work is negative. Volume increases. The work is negative. Well, how is it that I can be increasing the volume and the temperature can be decreasing as I increase the volume, yet the temperature remains the same the whole time? Thanks, heat. We have to add heat to this system as I increase the volume. So in this situation, heat is going into the system. I'm going to properly use my red pen now. Maybe this is where you've got an oven that you're putting your gas into, or you're just putting it in the sunshine, or maybe you're putting it above a Bunsen burner. But heat's going into this system, well, the volume is increasing. Same idea as before that we saw over here on the left. The work is going to be equal to the heat. The absolute values of those two will cancel out so that we can have an internal energy change of 0 and a temperature that stays the same the whole time. Additionally, I want to remind you, every single spot on this line, the temperature is the exact same number. Let's look at this question here. So the question I crossed out says, can heat flow during an isothermal process? Yes. Yes, it can. In fact, it has to. And we talked about those two examples when we talked about the volume getting smaller and needing the ice bath to achieve that, or the volume getting bigger and needing the fire to achieve it for that isothermal process. So next question, a closed sample of an ideal gas is taken through this cycle, A, B, C, D, and back to A, as shown in this PV diagram. At which of the points is the sample's temperature the highest? Well, we've talked about this a little bit, but I want to make sure we really nail this point home. The point that is furthest away, conceptual, just quick view, the point that is furthest away from the origin has the greatest temperature. The furthest away from the origin has the greatest temperature. If you wanted to do this in terms of ratios, you can also do a PV equals T scenario. I've seen a ton of multiple choice and free response questions where maybe they were label points as V, and maybe this is 3V, and this is P, and this is 3P, and they have you do comparisons at where is the temperature the greatest. And so you can kind of then use math to justify identifying your points. Last thing to talk about is adiabatic process. In the adiabatic process, no heat flows. No heat flows at all. So suddenly, our ice bath and our heat, our fire that we were using before, they're gone. Take these two cards, throw them at the wind, because now we don't need these anymore. The only way that we're going to change the internal energy of an object is by rapidly changing the volume. So let's go through these really quickly. Can an adiabatic process cause a change in temperature? Yes, it can. Definitely. So there's no heat. That's fine. I can still do a bunch of work. And by doing work, I change the internal energy. And by changing the internal energy, I change the temperature. And so as a reminder for yourself, maybe a note card moment, remember in an adiabatic process, we're saying there's no heat exchange. No heat transfer. But that doesn't mean we can't change the internal energy. One example that I have seen that people talk about is a bike pump. If you've ever used a bike pump to maybe air up a basketball or to literally air up your bicycle tire, you change the volume rapidly, and by changing the volume rapidly, you're doing a lot of work that actually changes the internal energy of the gas inside of the bike pump. During that process, however, you have no fire, you have no ice bath. All you're doing is rapidly pushing the piston, which will change the energy of the gas inside the piston. And so does heat flow? I'm looking at this second question. Does heat flow during an adiabatic process? No. Does the internal energy change? Yes. It's just that it's not isothermal. It's not isothermal. So just like before, we have a change in internal energy. That means we do have a change in heat as well, or I'm sorry, a change in temperature as well. So I'm going to even write myself that note. The temperature changes as well. Well, the last question, it's a good question. I really think that you can answer it. What is the difference between isothermal and adiabatic? You know what? I'm going to let you decide and come up with that one on your own. No, I'll tell you. Isothermal, no change in temperature. Adiabatic, yes, change in temperature. Isothermal, heat added to the system, yes. Adiabatic, no heat added in the system. You cannot tell by just looking at the graph. You need that information. You need that context about what's taking place between our isothermal and our adiabatic examples. All right, we're done.